Hello and welcome to ChemWonders. This lecture is a continuation of the previous lecture on aromatic substitution reactions. In this session, we're going to talk about a couple of more examples on aromatic electrophilic substitution reactions. In the previous video, a link to which you can find here at the top right, we discussed nitration and sulfonation reactions. Here we're going to talk about the Friedal Crafts acylation and alkylation reactions. But first let us discuss what Friedal Crafts acylation means. Friedal Craft acylation is basically the replacement of a hydrogen that is present on an aromatic ring by an acyl group. This is the general reaction for an acylation reaction. So we have the benzene ring as a substrate. This acid halide is the reagent which will provide the acyl group to this benzene ring. The reaction is carried out in the presence of a Lewis acid, that is aluminium chloride in this case, and water is added in the second step. The product of this reaction is a ketone with the formation of HCl as a byproduct. Let us see the general mechanism for Friedel-Craft acylation reaction. So what happens in the first step is that this acyl halide reacts with Lewis acids. Lewis acid, is an electron deficient molecule. This aluminium has formed 3 bonds and it is an electron deficient atom in this case. So this halogen from the acid halide, it attacks the aluminium in aluminium chloride, and as a result an acylium ion is produced. And you can see here there is a positive charge generated on the carbon atom of the carbonyl. But as you know, we have lone pairs on oxygen which can delocalize over, forming a triple bond between carbon and oxygen, and now the positive charge is shifted on the oxygen. So this positive charge is in resonance in this acylium ion, and AlCl4 is generated here. In the second step, the pi electrons from benzene attack the electron deficient carbon of the acylium ion, and as discussed in the previous examples of nitration and sulfonation, a sigma complex is generated here, and we have a positive charge now inside the ring which is in conjugation with the pi electrons of the ring, and that is why it delocalizes over and it resonates, it shifts its position throughout the ring, and finally in the second step water is added which acts as a base to abstract this proton, restoring aromaticity, and the final product, a ketone, is formed along with the formation of this hydronium ion. The hydronium ion then reacts with this AlCl4 minus to form aluminium chloride and water. So aluminium chloride is regenerated at the end, which means it acts as a catalyst in this reaction. Next is the Friedel-Crafts alkylation reaction. It's pretty much similar to the Friedel-Craft acylation, but it has a different result. So what happens in this reaction is that a hydrogen from an aromatic ring is replaced by an alkyl group. The product, that is the alkyl benzene formed in this reaction, is more reactive than the benzene molecule. It is because of the fact that alkyl groups are electron donating groups, and they donate electron density to the benzene ring, making it more electron rich and making it more reactive towards an electrophile. So aromatic electrophilic substitution reactions on alkyl benzene are much faster than benzene itself. So under the given reaction conditions, alkyl benzene will react more efficiently with an electrophile than benzene. So what can happen as a result of this alkylation reaction is that we have a more reactive product than the reactant itself, which can react further and give polyalkylated benzenes. So to avoid this multi-alkylation, benzene is used in large excess so that the aluminum chloride or the alkyl halide that is present can react with benzene rather than it reacts with alkyl benzene. This is a general reaction for alkylation reaction. So we have the benzene ring as a substrate. Alkyl halide is used as a reagent of alkylation. And again, we have a Lewis acid. The final product is an alkyl benzene with the formation of HCl. Let's see a general mechanism of Friedel-Craft's alkylation reaction. Again, in the first step, we have the formation of an electrophile. The electrophile in this case will be an alkyl carbocation. In the previous example, that is the Friedel-Craft acylation, the electrophile was an acylium ion. But in this case, we have the formation of an alkyl carbocation. You know that the bond between carbon and halogen is polarized, and the electron density is more tilted towards this halogen. And you also know that the reagent that we are using is a Lewis acid, aluminium being electron deficient in this case. So the halogen can easily attack the aluminium here, forming this AlCl4 negative, and with the formation of an electrophile that is an alkyl carbocation. In the second step, this alkyl carbocation is attacked by the pi electron density of the benzene ring. And again, as seen in the previous example, we have the formation of this sigma complex. Again, we have a positive charge that is delocalized or in resonance with the pi electrons still present in the ring. And so it delocalizes over and shifts its position throughout the ring. And finally, in the second step, with the addition of water, a proton is released, restoring aromaticity, and as a result, we have the final product that is an alkyl benzene with the formation of hydronium ion. This hydronium ion then again attacks the AlCl4 minus, forming aluminium chloride, and water molecule is released as a byproduct. So AlCl3 is regenerated at the end, and it can react with another alkyl halide if present in the reaction mixture to restart the reaction again and react with another benzene molecule. So this was all about Friedel-Craft's reaction. We have discussed alkylation and acylation in this reaction. Remember that the introduction of an acyl group deactivates the ring towards further electrophilic substitution reactions, while the introduction of an alkyl group to benzene activates the ring towards further electrophilic substitution reaction. So multi-acylation is not a problem, but multi-alkylation is a problem, because the product of acylation is less reactive than benzene itself, but the product of alkylation is more reactive. And we have also discussed how to avoid that problem of multi-alkylation. So this was all about aromatic electrophilic substitution reaction. In the next lectures, we will discuss some aromatic electrophilic substitution reactions on substituted benzene rings. So stay tuned, and thank you so much for watching.